Hello viewers, and you're welcome to Pop Proof's Advanced Physics channel. In this channel, we are dealing with one of the conservative problems in nature, and that has to do with gravitation. The force of gravity was discovered by Isaac Newton. As the story goes, he was sitting under an apple tree, and one of the apples fell on Newton's head, and he asked himself a very simple question. If the apple falls, does the moon also fall? And he was able to connect the heavens using that simple question. And later on, he was so fortunate that he was good at maths and he formulated the force of gravity in an equation. And in vector form, the force of gravity is proportional to the product of the two masses in the system. It could be the sun and the planet, or it could be any two objects at all. And it is pointed opposite to the unit vector. Let's just say this is one of the objects. Let me call that M1 and this is M2. There is a position vector going from the center of M1 to M2. Let's call that a vector R. So the unit vector R roof is also pointed in the direction of the position vector R. So if you want the force on M2 due to M1 is going to be the G times the product of the two masses divided by the magnitude of R squared, but pointed opposite. So that force will be directed in this, backward direction. That's why we have this negative sign here. Now let's rewind to the time of before Galileo Galilei and Kepler. Now, the view of the heavens that people held was that the Earth was the center of our solar system. So, if this is the Earth, before Kepler and before Nicolaus Copernicus, the view of the heavens was that the Earth was the center and all the planets, the moons and asteroids went around the Earth. This is before a man called Copernicus. And Copernicus was a Polish astronomer. But when he came, he postulated a revolution based on the observed facts of the heavens. That Copernicus said that it's rather the sun that is at the center of our solar system. So all the planets and asteroids and moons go around the sun. That is after Copernicus, Nicolaus Copernicus. Now, this is called the heliocentric model. Helio means sun, and centric means center model of the heavens. And of course, before Copernicus, this was called geocentric model. In fact, the heliocentric model, as proposed by Nicolaus Copernicus, received lots of criticisms, but Copernicus held on to this model, which has stood till today. And it was the ladder on which Newton stood to postulate or to formulate his gravitational law. Fast forward, based on the heliocentric model, there was a rich guy called Tycho Brahe. Tycho Brahe was a rich guy who had his own laboratory, and his student was Kepler. So Kepler worked in the laboratory of Tycho Brahe. It was an observatory called Uranus Observatory. And the telescopes could peep into deep space and they watched the planets and the moons move around the sun. So Tycho Brahe started tabulating a lot of data. He started to record a lot of the observations that he was able to make in the heavens. So he wrote down most of them. which later on influenced Kepler, who went on to see the connections of the data if he could come out with some laws based on the records that Tycho Brahe made to describe the motion of celestial objects. And Kepler was able to succeed, and he came out with 3 laws. And these 3 laws are the ones that influenced Isaac Newton. In other words, helped him to prove or to show that indeed his law of gravity was correct. So in this episode, we are proving the 3 Kepler's laws. Because it is an advanced physics class, we are going to show every mathematical proof of it. This is for Proof's advanced physics class. Kindly click on the notification bell, subscribe, share, comment, and like my videos. So the 3 Kepler's laws, I would summarize them as the first law. He said that planets revolve around the sun in elliptical orbit, but I will just put here elliptical orbit. So based on the data of Tycho Brahe, Kepler connected the data and saw that in fact the planets revolve around the sun in elliptical orbit. Ellipse is another word for oval. So this is an ellipse, which is another word for oval. You know, the Greeks, ancient Greeks, studied the conic sections, and an ellipse is one of them. The conic sections include parabola, circle, ellipse, hyperbola. And Kepler said the planets revolve around the sun in elliptical orbit with the sun at one focus. You know, an ellipse has a central axis and then 2 foci. You can also say foci. So the sun is at one focus and the planets revolve around it in that elliptical, orbit. That was his first law. And we are going to prove that mathematically. And 2, Kepler said that now a line joining a planet to the sun sweeps equal areas in equal times. So Kepler said that, so I will just call this equal areas in equal times. So Kepler basically said that if this is an orbit of a planet around the sun at one focus, then you have a line joining the planet to kind of the sun. Now this line will sweep equal areas in equal times. So let's give this planet a time, say delta t, and it moves from point 1 to point 2. Now there is an area formed by that line linking the sun to the planet. At the same amount of time delta t, if the planet say moves from this point 3 to say this point 4, and that line, which is elongated now, you calculate this area. Let me call this A1 and call this A2. Now he said that A1 was equal to A2. In other words, the change in the area with respect to time was or is a constant. And he was able to formulate this based on the data Tycho Brahe recorded. So that is his second law. And we're also going to prove that mathematically. Equal areas in equal times. Kepler's third law has to do with the period of revolution. Based on that data, he said the square of the period of revolution of a planet around the sun is proportional to the cube of the mean distance of the planet from the sun. So if you take a planet around the sun, then it revolves, it takes a complete revolution within a time period of t. Now the mean distance of the planet from the sun, we call it the semi-major axis, A, that the period squared was proportional to, or is proportional to, the cube of the mean distance of the planet from the sun. Once again, the mean distance is a semi-major axis. That is, if you take the central axis or the principal axis and divide the ellipse into two equal halves, this is called the semi-major axis, and it happens to be the mean distance of the planet from the sun. You see, the distance from the sun differs from point to point. If the planet is here, the distance is like that. If it is here, it is much longer one, and if it is here, it is much longer one. So the mean distance is the semi-major axis, which is A, and this is a mathematical formulation by Kepler. Now we are going to prove all these, not in this episode but in the next episode. Stay tuned if you enjoy Pop Proof's advanced physics class. Once again, subscribe to the channel so the channel can grow. Stay tuned.